Hi, this is Professor Gibson. Welcome to a video on Chapter 6, Section 1, Constant Percent Change. All right, so the question for this section really is, what kind of function gives us a constant percent change? Okay, so what we mean by that is, like for example, it's a function where things change over time, that the percent change every year or every month or something would be the same. Not that the amount of change would be the same, but that the percent change would be the same. Okay, so the first question is, well, what kind of function gets us that? All right, so let's look at this one. Here we'll look at a line, okay? Use a relatively simple one, y equals 2x, all right? So I've written the chart in over here. So x is 1, 2, 3, 4, y is 2x, so it's just double that each time, right? 2, 4, 6, 8. The question for that is, what is the percent change then on these? Okay, so let's look at it. So first we'll do the percent change from 2 to 4. When y is 2 to y is 4, right? X goes up by 1. So remember our percent change formula here is the new minus the original divided by the original times 100. All right. So the new, in this case, since we're going from 2 to 4, the new is 4. The original was 2. Divide by 2. Multiply by 100 to turn it into a percent. All right. So that ends up equaling 100%. All right. So the y from the first year to the second year, from x equals 1 to x equals 2, increases by 100%. Well, let's move down here a little bit. What about from the year from x equals 3 to x equals 4? Well, y goes from 6 to 8, right? All right, so the new this time is 8. The original is 6. Divide that by 6 times 100. This is 2 over 6 times 100. This turns out to be 33.3%. It's not the same, right? It changed. And in fact, if we were to follow this on down, the further we go, the smaller the percent change gets. So it's not a line. Well, what is it? What gets me constant percent change? Let's try something else here. You remember we wanted to increase something by a set percentage. Like let's say we got an amount of money invested, we're going to increase it by 8%. Right? So we've got $20,000 somewhere invested. We want to increase it by 8%. Remember, we multiply it by a factor, and for the factor, we do 1 plus the 8%. So 1 plus 8 would be 1.08, right? So taking an amount of money, or anything else really, multiply it by 1.08, that's going to increase it by 8%. Well, what if we wanted to do that constantly, like every year? Well, I guess we'd have to multiply by 1.08 every year, right? Just keep doing it. Well, how would we write that out? Well, it's 20,000. And then times 1.08 to the t, where t is the number of years we want, right? Now this goes on. So this is my function. This then would increase by 1.08 by 8% every year for however many years you want. Just stick that number of years you want, just stick that number in for t. Well, what kind of function is that? Well, it's compound interest for one, but in sort of the broader term, it's an exponential function. All right, exponential functions are functions that grow or change really, because they could decrease, change by a constant percent interest. And the terminology is, see if it's going up by 8%, we would multiply by 1.08. Remember, it was going down by 8%, you would subtract the 0.08 in the factor, right? So then your factor would become 0.92. Okay, so this would be the factor you use if you're going to decrease by 8% per year. So what happens then is if the factor is bigger than 1, you get growth. If the factor is between 0 and 1, you get decay. Okay? Now, just a quick reminder, because it looks like we're going to be using compound interest mostly as our examples. Our text likes financial stuff. Reminder on the compound interest formula. A is the amount, right? P is the principal, it's the original amount you put in. R is the interest rate, is the annual interest rate. Okay, R is annual interest rate. N, N is the number of times, or the number of compoundings per year. In this section, it's kind of nice because, or they make this a little bit simpler for us, less complicated, because the N is usually 1. So we can kind of ignore it because dividing by 1 and multiplying by 1 doesn't do anything. And then the T is the number of years. All right, A is the amount, like the amount at the end of however many years. P is the amount you start with, it's the amount you invest. Everyone put that. Okay? All right, we've got a little bit of a reminder on that. So let's look at the next thing here. Let's say a student deposits $500 into an account, and deposit $500, paying 6% interest for 5 years. 6% interest, 5 years, going to compound annually. Calculate how much money this will be worth after 5 years. So I did this in a little table over here. The function is 500 times 1.06 to the t. Really, if you did 1 plus 0.06, right? So 1.06 to the t. The first year you start with, at the year 0, you have $500. At year 1, you take that 500, you multiply by 1.06, you get 530. At year 2, multiply 1.06 again. So we take our 530 times 1.06, that's another 6% increase up to here. Year 3, we want another 6% increase, right? 6% per year, right? We multiply 1.06. Well, so what's happening? We keep, the way that I did this, we've multiplied by 1.06 every year, right? So this first time, I multiplied by 1.06 one time, that's 1.06 to the 1. Now the second time, for year 2, I multiplied by it in year 1, and now again in year 2. So I've really done is multiply by 1.06 twice, right? And then here in year 3, I've multiplied by 1.06 again. So now 3. So now in these last 2 years, I just wrote it to the power, right? 500 times 1.06 to the 4th gets me this, 631.24. Same thing as taking what I had in year 3 and multiplying by 1.06. And then in the year 5, 1.06 to the 5th. Okay, so exponential function like this, right? A number times a number to a power. It's exponential, right? Again, a number called the base times another number to a power is exponential growth. And that, this number right here, is where you get your constant percent change. In this case, the factor 1.06 minus 1 would get us 0.06, which is a 6% change every year. All right? So, constant percent change, essentially, right? So what we've seen is that constant percent change means multiplying by the same factor every year, and that turns out to be exponential. Okay? All right, let's do one more example here, show some things. Compare the exponential growth equation, p equals 500 to 1.06 to the t, with linear growth that starts at 500. Okay, so what I did here, this is really the same equation from we were just doing up above. The one above I did at years 1, 2, 3, 4, 5. Here we're going to take the same thing and we're going to do it over further time. And we're going to compare it. So you remember from before when we did interest, there's a couple kinds of interest. One kind is simple interest, it's the same basically as linear. It's like a line through the graphic. Okay, so simple interest, if we want 6% of 500 is 30. Okay, so going up by 30 every year is 6% simple interest, right? Year 0, we'd have start at 500. Year 1, we've got 530. Year 2, we'd have 10 times 30 is 300 plus 500 would be 800, right? And so on. So what happens here is every time you go up 10 years, you go up $300, right? The amount you increase is fixed. The percent is not. Now over here is where the percent change is fixed. Okay, we can put the zeros on here if you want, have the same format. So we started at the same spot, year 0 at the beginning, $500. First year, 6% is the same thing, 530. After that, it begins to go up faster, right? Year 10, after 10 years, on the simple, we'd have 800. That's linear growth. On 10 years, on the exponential, we'd have $895.42, right? And you keep doing this, the longer time goes on, the bigger difference it makes, right? After 40 years, in the simple interest, we'd only have $1,700. In the compound interest, we'd have over $5,000. And you know what? The bigger the interest rate, the more difference this makes too. If this had been like 12% interest, this would have been a very large amount of money. Whereas 12% in the simple interest, it would have just been 2,900. Okay, all right. So that's a little bit kind of comparing and contrasting exponential growth versus linear, and showing us that exponential growth is constant percent change. Okay, that is it for this one. I hope you found it helpful.